Thank you, Alvaro, and welcome to everyone coming to this talk. So the concept of big data I'll talk briefly about. There's been a lot of it this morning, and I'll talk briefly about non-stationarity, but very few people have addressed what I mean by non-stationarity. A process is stationary if its distribution doesn't change. It is otherwise non-stationary. Everything in reality, in observational data, is non-stationary. There is no getting away from it. Nothing stays the same in the world. Not even first moments, not first moments of changes, not the variance of changes, nothing. It's all change. That's the whole point about the world. It is nothing like today than it was 100 years ago, or 1,000 years ago, or 10,000 years ago. Enormous change over time. And unless we deal with non-stationarity, big data will always come up with the wrong answers. So if you seek to establish substantive relationships among vast numbers of spurious connections by modeling big data, you've got to find what really matters from what doesn't matter. And this is where non-stationarity is a tremendous problem and a tremendous benefit. Because everything's changing, things do not stay the same connection, and therefore you can rule out large numbers of the spurious connections. So big data will be useful if and only if it can increase the probability of nesting what is actually going on inside your model, so you can find what is actually going on. It can increase the power of tests, but not necessarily. A lot of big data can reduce and be junk. But it also hugely raises the chances of adventitious significance, things turning up by chance. And simply choosing the best fitting equation or trying hundreds of empirical fits, as I often see, and picking the one you like, perhaps contradicted by others that you didn't bother reporting because you liked this one, you didn't like them, it's not going to lead to a useful outcome. But the fact that some approaches are bad doesn't entail that all approaches are bad, and randomly digging holes doesn't compete with geology-based searches for minerals. Similarly, you can undertake statistical modeling by mining big data productively, but it's got to take account of wide-sense non-stationarity. And by wide sense, I mean stochastic trends and location shifts. The distributions are shifting, both because they're trending stochastically and because things suddenly alter. So here's the route map. It's far too long. I'll probably have to drop bits of it to get through it in time, but talk very briefly about big data and co-integration. Then I'll talk about the fact that because it's enormous, everything's got to be automatic. There's no way you can deal with it as individuals. You've got to automatically form models, treat their dynamics automatically, non-linearities automatically, outliers and shifts automatically. Then you've got to do automatic model selection, and you've got to do it in such a way that you can handle many more variables and observations, huge numbers of both, and tackle multiple shifts and co-integration. You've got to automatically evaluate the model. You can't go back and suddenly start checking up at it. And one sees remarkably little of that in the literature. And then there are big computational issues. And I hope to end by showing you just how tiny computational issues are for even quite big data, as we'll get to, and show you how bad stepwise and lasso are in the kind of situations you face in economics, and compare that to what happens when we're looking at co-integration. Now, big data differ greatly across disciplines. Nobody this morning talked about the use of photographs in areas hit by a tsunami to find out where the survivors are. There's qualitative data, there's binary data, there's general numerical. Even within general numerical, there's huge, many variables, many observations. Fat, many variables, not so many observations. And tall, which was the high frequency stuff, not so many variables, but many observations. In which way you treat them differs. And it also depends on whether it's cross-section, time series, or panels, and every discipline's facing different sets of problems. And I'm mainly going to address observational data in not just economics, actually. That's also climate, using automatic model selection when fat data are not too big. So we'll have more variables and observations, but we're not talking in millions. Now, our data to start with are very problematic. All of our data are approximate measurements, are subject to revision, it's high dimensional, it's evolving, it's intercorrelated, it's probably nonlinear, and it's certainly prone to abrupt shifts. To represent such a non-stationary process requires models that account for all the substantively important variables. Because the key thing about wide-sense non-stationarity is if you leave out things that matter and they're non-stationary, your model will continually break down, right? It'll be shifted by things you haven't got in it. So you need them all in. It's not a matter of just picking a few variables and hoping for the best. I'm afraid you've got to have very big models, and if you've got big data, that's at least possible. We cannot possibly know the correct specification in observational data, so the models must always be data-based on available samples to discover what matters empirically. And can automatic methods applied to big data help? Well, Hull variance using the wrong methods, but at least he agrees with the answer. Yes is correct, and there are many potential predictors, so you do need to select, but large data sets allow for more flexible models. Now, will cointegration matter? Well, cointegration matters, I think, more when it's not there than when it is in big data. We know the origins and debates about the viable links between levels and differences in time series. And we also know that most observational time series have got both stochastic trends and unit roots. And of course, it's been my complaint about time series methods in climate for a very long time that they don't seem to realize that they're dealing with highly non-stationary processes and that the methods of inference have to differ in that context. But in big data, if you've got big T and small n, we don't actually need to do anything. If there is cointegration, it's automatically there. If it's not, you need to difference. Once you've got it to I0, outliers can matter. Graham Myson and I show that you can get completely the wrong answer if you ignore outliers in modeling I0 variables, having reduced them through cointegration. And location shifts always matter, and have long been part of the concern about how you formulate deterministic terms for valid inference. Now, there are roles of cointegration in testing theories, in modeling empirical evidence, in forecasting, and in policy. Now, if theory does entail long-run equilibria, and it's always been an infuriating feature of DSGEs, they don't bother testing if their assertions do cointegrate. But it's beginning to turn up in climate with Felix Prettis doing a really interesting paper showing that energy balance models of Earth's climate can be based completely in observational data because the cointegrating vectors correspond to the laws of conservation of energy. And of course, if they didn't, you'd be really worried, right? Because that's how the IPCC build their models. So imposing valid cointegration generally helps clear interpretation. The advantage of having empirical models in climate, by the way, is it's much easier to deal with the impact of volcanic eruptions, with a big change in El Nino, with sudden changes in CO2 emissions because China's built 45 million more coal power stations or whatever than it is in the big models. We can very much deal with that rapidly. And the lack of cointegration is important, that you do get nonsense regressions if there's no long-run links, but you're analyzing things in levels. Now, cointegration has never helped in forecasting, I have to tell you, apart from the first paper by Rob Engel, which we showed was a fluke. It just doesn't really matter in forecasting, because forecasting is about a future being different from the past, and cointegration mapped into equilibrium correction can be the worst possible method of forecasting when the world shifts, because your model, as we've seen with DSGEs through the financial crisis and after, the model desperately tries to get back to its inbuilt equilibrium. And if that equilibrium is shifted, it keeps going back to the wrong target. So if you look at the budget for the Office for Budget Responsibility in Britain, OBR, they have these fantastic graphs, we call them hedgehog graphs, of predictions of Britain's productivity growth. And productivity growth has done this, and their graphs are like this. It looks like the spines of a hedgehog. And of course, that's because their model has inbuilt the past trend in productivity. And so long as it keeps trying to get back to that trend, it will keep going wildly away from the data. You don't want those kinds of models for forecasting. So cointegration, big data or small data, shouldn't be playing a role. But if you want policy, you've got to have it, right? Because policy is all about these long-run connections, not the short-run partial derivatives. And so you need a robust forecasting model that retains the equilibrium correction component. And please, 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 Alvaro, Juan, Jesus, don't call it error correction. It does not error correct. It equilibrium corrects, and that's a disaster when the equilibrium shifts. If it did error correct, it would be fantastic. It would always correct our errors. But no, it doesn't, and I'm afraid it never will. We do need to invent error correction mechanisms, and I'd love the name to be free for whoever happened to be brilliant enough to discover an error correction mechanism that actually fixed your error, rather than an equilibrium correction mechanism that always went back to the inbuilt equilibrium in the model. Now, in separate work, we've shown that big data often have big measurement errors. It's unclear if these matter for big N, for laws of large numbers, but in wide sense non-stationarity analysis, they don't tend to matter because the trend dominates and the location shifts dominate. And although the data are mismeasured, if we suddenly do this, you can see the connections. Now, what about systems? Well, I don't think we'll ever get round to doing a million-dimensional endogenous variable systems. Partial systems seem to be the only possibility, and even then, with small numbers like 10 variables, you're going to face three problems: that shifts in the system might show up in many of the subsystems. You've got two methods of handling that Taka Kurita and Bent Nielsen are looking at. If it's a partial system, it's an open system because you haven't got all the variables in it unless you've deliberately closed it, and that's the advice that Graham Misen and I have. You should just deliberately close it. Forget if you're running, say, the British economy and you've got a model of the UK economy, and then offline you're forecasting the US dollar exchange rate, output in the world, oil prices, etc. You're wasting your time. You have to be fantastically good at that to do better than to throw them away. And you see this showing up dramatically in the climate literature, where people regress GNP on temperature, right? And then they use that to predict what future GNP changes will be. Now, GNP is not generated by temperature. GNP is generated by people working on capital, putting in inputs, etc. But if you actually wanted to see that, you'd have to model the whole system and forecast how temperature would affect labor inputs, how it would affect material inputs, food inputs, etc., etc. Whereas they just shortcut it and throw away everything except the one variable of interest. And then Tony Espaza and his co-authors have shown the benefits of imposing common factors in forecasting, which is a bit different from ours. Then if you're dealing with very big systems, you've got multi-step interval forecasts, you've got to evaluate them, then you're always going to have more variables than observations over the forecast period of any reasonable forecast period. But that can be dealt with, again, by methods similar to the ones I'm going to show you shortly. So there are 5 key big data difficulties. Can we calculate the probabilities of false positives, that is, garbage coming out of it, and set a significance level to control things at desired magnitude? And we'll use the concept of gauge for that. Can we handle multiple location shifts by indicator saturation if n is not too large? I'll do that live at the end and show you doing it when the sample size is 5,000 and the number of variables is 6,000. And yet you can deal with these sorts of issues. We can test causation when the world changes by evaluating superexogeneity. Cross-section stuff, I think, is hopeless in economic. I mean, I'm terribly sorry for those of you who do cross-section analysis, but it's completely biased. You cannot get a sequential factorization in a cross-section. And so hidden dependence is a fundamental problem and is showing up in fact, the recent paper by Angus Deaton and Nancy Cartwright saying it's a really, really serious problem. But if you have a theory, we can retain it. Whether the theory is right or wrong doesn't actually matter too much. We retain it. If it's right, you'll get back what you would have got by just fitting it. And if it's wrong, you'll find you're wrong. So you can actually make genuine discoveries even with vast numbers of spurious patterns. And I'm going to show you there are vast numbers of spurious patterns. Now, this is no different from the basic fundamental problem of all statistical analyses of observational data. How do you avoid concluding with a substantively misspecified model or at the extreme, a spurious relationship? In my talks on climate, I show that if you plot the world's CO2 emissions and you put through it the British data on the retail price index, it's an almost perfect fit. Right? There's just an update in Alvaro's comment on inflation and rainfall. Here it's CO2 and using the price index. But if you look at the differences, they're completely uncorrelated. So these 5 problems must be successfully resolved. And this is going to require automation comes in. To formulate it with all the substantively relevant variables is an enormous problem unless it can be done automatically. To specify the form of model is quite difficult unless you've got a very general form that you think might characterize what's going on. You've then got to select, eliminating irrelevant variables for retaining relevant. You've then got to evaluate, check the model is well specified, and there is this computational problem. So let's look at automatic model extensions. We want a congruent, undominated model. That is a model that no other model can explain the results of it and not be explained by it, and that it characterizes the data up to the characteristics you're interested in, IID errors or whatever. So we need to know which variables are actually relevant, what their lagged responses are, functional forms, outlier shifts, unit roots, cointegration, endogeneity, exogeneity status, and they've all got to be embedded in a model specification that satisfies requirements for valid inference. And we have to tackle all these jointly. And that's going to require automatic inclusion of all the candidates, all the lag lengths, all the nonlinearities, all the outliers, all the parameter shifts. Automatically handle more variables and observations, because in our approach, you always have it, often by orders of magnitude. In today's empirical illustration that I'll show live, there's not many more variables and observations. There are some, but we've done up to 50,000 variables and 120 data points, and came up with an answer that allowed a large American insurance company to survive the financial crisis. So you can do it even in huge numbers of variables relative to observations. You need a high probability of success in retaining most of the relevant but few of the irrelevant, and you need automatic evaluation. And all of this is embodied in autometrics, which is part of PCGive rather than PCGets these days, but it's just the next successor. And this is the book you need to read. It's an MIT Press book, Empirical Model Discovery and Theory Evaluation, done jointly and simultaneously by automatic selection methods by myself and Jürgen Dornick. So how do we proceed? 3 extensions. Get a sequential factorization so you can do valid inference. Functional form transformations for nonlinearity. Alvaro was right, I'd talk about it. And then impulse and step indicator saturation, respectively, for outliers and shifts. I'm not going to talk much about indicator saturation. It's a whole talk on its own, but we design indicators for particular purposes. So impulse indicators for outliers, step indicators for location shifts. We've designed indicators for volcanic eruptions, for multiplicative changes in parameters, for changes in trends, and so on. So creating S-lags, dead easy, create S-lags. That the program can do that in a second, and you need that to get a martingale difference sequence for valid inference. I'm not going today to look in partial systems, but we're writing a version of autometrics that will automatically handle your partial system, right, rather than just your single equation. As Alvaro noted, Jenny and I have proposed using squares, cubes, and exponentials of the principal components. And the reason for that is because all the variables are intercorrelated, each principal component is a linear combination of almost every z. So when you square an individual member of a principal component, you get all the squares and cross products of all the z's. So you get a very low dimensional way of approximating nonlinearity. There's no collinearity between the elements of the U's, and it includes many important sources of departure. You get the quadratics, you get the cubics, and you get the exponential type functions. And the reason for it is if we're going to be dealing with 5,000 variables, which is the end right-hand side top where k is 5,000, the number of general cubic polynomial plus exponentials is 2 times 10 to the power 10. That's just a little bit big even for big data. Whereas if you use our method, you've only got 15,000, right? It's big, but it's not huge. And if you came down to just 100 variables, you'd only have 300 extra nonlinearities to add in rather than 176,000. And then finally, we're going to put in an impulse indicator for every observation. And this dates back to work with Sir in 2008. Showing that it's quite feasible. And I'm not going to walk through the theory of it again in a talk like this, but you put in half the indicators as an illustration of how it might work. That dummies out the first half of the observations. So you get unbiased estimates of the parameters from the second half. You also get an estimate of the significant indicators in the first half. So you record those. Then you drop the first half indicators. You include the second half. You record again. Then you combine the selected indicators. And on average, with 100 observations and a 1% significance, you'd get rid of one observation. So here you've tested for breaks of any form, any magnitude, any sign, anywhere in the sample, and it's cost you one observation. You tell me what method is better than that. Now, there are 5 examples which are well-known but inefficient variants of impulse indicator saturation. I see people doing recursive estimation. That's impulse indicator saturation over future observations, adding them back in one at a time, but not looking at what they look like before you get there. Moving windows is almost exactly the same. Hold back is IIS over the excluded data points. Excluding data implicitly use these impulse indicator saturation, which is where I discovered it. And the Chow test is an IIS on a specific set of data. And all of these work if and only if you know the rest of the model. The whole point about our method is you don't need to know anything much about the model. You just need to know what variables to search across. So you can include IIS in a general selection procedure. So now we've got everything. We've got our candidate variables that you've decided on. We've orthogonalized them. We've got their lag lengths. We've got all their functional forms. We've got all their outliers. And then we get this massive general unrestricted model with up to maybe 50 lags, which is the example I'm going to use, and 20 variables. So there's 1,000 in the very first term alone there, never mind all the others. And I'm not going to put the others in. I will put in the lagged y's, which just takes it to 1,050, and then I'll put in 5,000 indicators, which will take us to 6,050 variables for 5,000 data points, and I'll run that through for you live. Many special cases, I'm not going to walk through that. So we've now automatically set up the model, and the program can do that in seconds. Then we can look at the properties of automatic model selection, how we tackle multiple shifts, more variables and observations, and retaining theory variables. And the key issue that's totally confused in most of the statistics literature I read is not distinguishing between the cost of inference and the costs of search. And the cost of inference is if you start with the actual data generation process, and you then want to carry out tests on what matters and what doesn't matter. Now, no test has got a 0 null rejection frequency, and very few have got unit rejection frequencies and the alternative, so you will make mistakes. And indeed, if some of the relevant variables have small t values, you'll never include them. So we can measure the costs of inference by the root mean squared error on the estimated, simplified data generation process after you've done whatever method of model selection you're doing on the data generation process. Now, we set up a vastly more general, unrestricted model which nests, we hope, the data generation process, and then we've got to search across it. And that will sometimes, but not always, actually increase the root mean squared errors for the relevant variables when starting from the general model as against the data generation process, plus the costs of retaining irrelevant variables. So gauge is empirical null retention frequency of a selection procedure. How often does it keep the irrelevant variables? And potency is the average non-null retention frequency of the relevant ones. How often do you actually find what matters? And the whole point behind autometrics and the way we try to set it up is we'd like to select the same model starting from our hugely general model as you would starting from the data generation process when we both use the same significance level. So we both agree to use 1 in 1,000, we'll end up at the same place. And that tells you I don't need to know the data generation process when I start. Right? And that's very important in a complicated science like economics or climate. Moreover, if you have got a decent theory, Søren and I had a paper a couple of years ago showing you can avoid all inference costs, I mean all inference costs, for valid theory parameters by embedding the theory, but not searching across it, while you search across all the putative relevant variables. And if you are correct in your theory, you'll get back exactly the numbers you would have got if you did no search. And if you're not correct in your theory, you'll learn you're not correct in your theory. So it's a win-win, and that's what the book is much about. So don't bother with the top part, just read the bottom part. The bottom part where k equals n alpha, the two ends of equation 3. The number of null variables retained when every variable is irrelevant and you're doing t-testing at a significance level, alpha, is n alpha. So you've got 1,000 variables and you're using 1 in 1,000 significance level, you will keep one irrelevant variable. Now, there are 2 to the 1,000 possible models out there. That's what you're searching across, 2 to the 1,000 possible models. And you can't actually do that. It would take longer than the lifetime of the universe, even using the world's fastest combinations of online computers. So you can't do it, but that's what you would have to do. And nevertheless, you'll end up keeping one irrelevant variable. Now, the statistics literature gets it all wrong, because every time you do a Monte Carlo simulation, it'll be a different one. So you'll end up with 1,000 different models. But of course, they're all irrelevant. It's just the only thing that's relevant is you've kept one irrelevant variable, right? That's what matters. The fact that you'd pick a different one in every trial by chance doesn't matter at all. Model uncertainty is not a useful concept in this context. So if we start off with my case, roughly n is 5,000, alpha I'm going to use 1 in 10,000, you'll keep half a variable, despite the fact there are 10 to the 1,500 possible models out there. Just so large you can't even begin to think about it. And at n of 100,000, well, you'd keep 10. But then you've started not knowing anything about how 100,000 variables are connected to what you're doing, and you've found that 10 of them, by chance, might be. Now, why can this work? And it can only work by coming back to roughly what Søren was saying. You need a model. And the model we have here is the normal model. You might think it's very odd using a normal model in wide-sense non-stationary data, but I'll justify that because we take out all the non-stationarities, and what we're left with, after doing impulse indicator saturation to remove all the nonlinearities, sorry, all the outliers, is approximately normal. And so right at the end, the right-hand column, 2 times 10 to the power minus 7, and alpha that small, the critical value is 6, according to Selby's calculations. So even if you had 5 million bits of rubbish in your model, if you use a critical value of 6, which is not that tight when you're looking across 5 million bits of rubbish, you'd keep one of them by chance, right? So the chances of getting spurious results are near 0 if you set about it properly. But it does rely heavily on normality, so you must remove shifts, outliers, asymmetry, fat tails, etc., to ensure, and of course a sequential factorization to assure the errors are essentially martingale difference sequences that are homogeneous over time. Right, can we keep the relevant variables? And the answer is, well, that's where big data might help us if the variables are relevant and we can control for shifts over time. Then 10,000 variables, sample size of maybe 100,000, t-value of 6 is not terribly demanding. We can use 1 in 10,000 as our critical value, our significance level. It's a critical value of 4. Your chances of keeping variables with t's of 6 is 0.976. But the final right-hand column is the key one. You're not looking for one variable. You're usually looking for a number of variables. And the probability of keeping all of them drops dramatically relative to a single one. So even if the chances of 1 are 0.996, the chances of 4 are 0.984, and the chances of 8 are the square of that. So that it's going to be quite difficult to keep all the relevant variables. And that is a problem with big data, and therefore it will pay you to do things to reduce the big data from the outset. Then, brilliant work by Søren and Bent Nielsen have shown that the gauge is close to the selected alpha for a small alpha, and have done the variance of it. We show the potencies near the theory power of a one-off test at the same non-centrality. We never look at goodness of fit. There's no problem but repeated testing, and it can be generalized to likelihood and IV if necessary. Now, when there's more variables than observations, you've got to divide it up. You obviously can't fit it. So you can divide it into m sub-blocks that are smaller than, at most, half the sample size, and you set alpha as 1 upon n, and then you search across blocks, and then across blocks of blocks, and then across mixes of blocks, and I'll discuss that when I come to computation. And Artometrics groups variables into those already selected and those not selected. And crucially, Those that are already selected might get dumped later because they're just picked up by chance until the correct ones comes in, and those that are not yet selected might be picked up later. One-step searches are not going to work. You need block searches, and quite big blocks. So retaining theory variables, if you've got m theory-relevant variables to be retained and t is bigger than n, that's a nice simple case, just orthogonalize the other n minus m variables with respect to them because you don't think they matter, and then retain the m variables at every stage and only select over the other n minus m. And under the null that your DGP includes precisely those m, despite selection, you'll get exactly the same estimated coefficients of relevant variables and their distributions as if you knew the truth before you started. And that's not something that, in general, you can rely on in economics. But if you've got more variables and observations, you just have to do it in blocks. It's not a big deal. Automatic evaluation, well, we run through all the usual things, checking that the model is indeed congruent. We check parsimonious encompassing. Now, a big way that Autometrics differs from other programs is that it does check that the errors are well behaved, and it does check you've lost no significant information during the reduction from the starting point, even in the case that you've got searches across more variables and observations. And it backtracks if it does show that you've lost information to find lost it, and whether you can find a valid, less reduced model on any earlier path. Now, we conduct all inferences as if it was I naught critical values, and all inferences as if they were normal. So you do need to make sure that those hypotheses are correct. There's no way to do automatic model selection using sort of critical values for an exponential distribution or whatever. You've got to know what is going on in such a form you can reduce it to use I naught critical values. Otherwise, it can't possibly select correctly. Then at the end, we test parameter invariance under regime shifts in order to ensure you don't get serious misprediction. That's super-exogeneity. And long back, Carlos Santos and I showed a test of doing it, and it's got the right size and the right power relative to other tests for looking at it. But more recently, Jenny Castle, Andrew Martinez, and I have suggested it's much better to use a step indicator saturation test, but that's actually too computationally expensive for 6,000 variables. It just takes days to run it. But if you've got days to wait, then you can do it. So it's very simple. You look at the distributions of the marginal variables, the z's. You find out where they go wrong, where the models of them shift. You then add those shift indicators to your conditional model of y given z, and you do an f-test, a one-off f-test. And if they matter, your model does not have invariance. And if they don't matter, then despite the behavior changing in the variables that you're using to explain y, you don't change the relationship between y and z. And so big changes in z have the same impact on y as small changes in z, and they remain constant over time. So how am I doing? I've been okay, am I? Plenty of time at this stage. 15 minutes, excellent. Right. So Autometrics is a tree search algorithm. So imagine you've got a cat in a tree and it's walking along a branch and it walks on another branch and it diverges in another branch. And eventually it gets to a branch it can't stand on. That's a tree search, right? The cat then has to be taken down by the fire brigade. Now technically, we're selecting congruent, parsimonious, encompassing models. They've got to have all three properties. We want them as small as possible without losing information on the general model and yet describing the data up to a white noise, common variance, constant variance type process with constant parameters. And implicitly, all 2 to the n models need checking in a tree search. If it's going to search the tree completely, it's got to search all 2 to the n branches. And that's impossible for large n. There isn't time in the universe. Now, circumventing strategies use non-statistical criteria to restrict the variables to be selected over. If I was modeling the world's CO2 emissions, I would not include the UK's retail price index data in that because it's obviously not very relevant. You can search subunits separately, and when all candidate variables are mutually orthogonal, as happens with impulse indicators, then you can do one-cut selection without much trouble. You can use holdback and fit subsamples over time, and so on. There's quite a number of things but you're still going to have a big computational problem. So even for n of 100, and that's tiny by modern standards, there's 2 to the 100 possible models, that's 10 to the 30. And even if you could compute 10 to the power 10 models per second, that would take longer than the age of the universe, right? You're never going to get there. Now, single-step searches like Lasso can get through it quite quickly because they're not looking at all possible models. They're only looking at one-step forward models. But we can magnify that sensibly by looking at blocks of m variables at a time. So with in-block searches require 2 to the m paths, then you're going to repeat them n over m times, because there's that number of variables, that's the number of blocks you have to search over. And then we're going to mix and match the blocks and rerun r times. And so in the end, we'll have 2 to the power m times n times r divided by m searches. So if we look at the n equals 100, and we take m of 20, and we mix them 50 times to make sure we get almost all the possible kinds of combinations, that's only 10 to the power 8, and you get the answer immediately, right? So despite the same problem, the computational method really matters greatly. The computational cost is the complete subsearch within the tree. The statistical cost of not doing that is overly small submodels, and we admit that autometrics will miss some models because it cannot possibly search all of them. But it does a pretty good job in searching across very large numbers. So here's an illustration, first of all on orthogonal data, then on intercorrelated data, and then on cointegrated intercorrelated data. So if we take a data generation process for 5,000 variables, 20 observations, selecting at alpha of 1 in 10,000, and we just run on the 20, it gets the answers almost immediately under the null. Then we create up to 1 lag, just to show that that makes no difference, and then 50 lags, which takes us to 1,000 variables. And then we're going to add 5,000 impulse indicators, so we get 6,000 variables. And that now gives us a serious computational problem, 6,000 variables fitted to 5,000 observations. When S is 1 and we do impulse indicator saturation, plus, so we've got roughly 5,000 in total, selection takes 4 minutes in a PC, and it correctly selects the null models. It's now 11 seconds in version 8. When we get to 50, it used to take 11 minutes, now it just takes 3 minutes. If we do 2 without pre-search, it used to take 15 seconds, but in fact now takes 22 seconds, it's slightly longer. And if we look at S equals 50 and impulse indicator saturation, so we've now got 6,000 variables with 50 blocks of approximately 100, it now takes 12 seconds, but it keeps one irrelevant variable. So moving from n of 1,000 with pre-search to n of 6,000, that's case 2 to case 4, we come down from 3 minutes to 12 seconds. So it matters how you set the problem up. We then rerun these experiments with 10 relevant variables, keeping the same significance levels, and their coefficients range from 0.075 to 0.175. That's non-centralities of 5.3 to 12.4, which you've got 5,000 observations are not particularly demanding. And that maps to a C alpha of about 4. It gives you a 97% chance of retaining the variable with the smallest non-zero coefficient and 1 for most of the others. So again, 1,000 simulations, S of 1 and impulse indicator saturation, just 11 seconds, and it gets the right answer. S of 50, without IIS, still takes a lot longer, 2.5 minutes, and that's because it's not forced to do block searches, and it's the block searches that really reduces the time. It's very slow if you do a full tree search. We've got that down to 27 seconds. If we do IIS, it used to take 12.5 minutes. Now it takes 15 seconds. It selects 9 of the relevant and it misses the one irrelevant. If we force the correct retention of all 10 relevant and do searches, it now takes 14 seconds and keeps 1 irrelevant. Excuse me, but only because it fails encompassing, not because the irrelevant is significant. If you retain 5 relevant and 5 irrelevant, i.e. you've got completely the wrong theory, it now takes 27 seconds. You find the DGP, but one of the 5 forced irrelevants is significant at 0.005, but not at 0.001. If we repeat that in version 8, it missed 2 relevant and finds 1 forced irrelevant, but just took 14 seconds. Now, if they're all intercorrelated, and here I've intercorrelated them in pairs of plus minus 0.25 all the way up to plus minus 0.35. Non-centrality is now 7.7 to 10.8. So notice, despite the intercorrelations, the non-centralities have got bigger with the same coefficients, but the correlations are tiny. The biggest is of the order of 0.035 and minus 0.037. So despite t equals 5,000, none would be significant individually. If you started stepwise, it would stop. It would find nothing. But if you jointly include all of them, then the 10 relevant variables are significant at 1 in 10,000 in the model. So the largest correlation here is Z4. And mimicking one step, let's add that, but it's only significant at 0.005, not 0.001. And importantly, if you add the next highest correlation, nothing significant, and stepwise stops. Stepwise is unwise. Don't use it. There's a number of stupid computer programs out there give you stepwise regression for model selection. It's a disaster, and you should never touch it with a barge pole. What about Lasso with cross-validation? Well, it's the same problem. Lasso can't possibly handle data like this. It's not designed to, but they haven't thought about it. So if we set S of 0, 20 variables and intercept, it finds all 10 relevant, but it doesn't shrink to 0, 8 of the 10 irrelevant. And when we get up to 50 lags and 1,000 variables, yes, it finds all 10 relevant, but it now retains 167 irrelevant variables, right? It works quite quickly. Most of these took 53 seconds. I couldn't attempt to do lasso and impulse indicator saturation because it doesn't have an automatic method of creating 50 or 5,000 impulse indicators, but the other results are so bad it didn't seem worthwhile. Let's go to cointegration. Now, the Z's are random walks. Y is cointegrated with 10 of the Z's, but not with the others. If S is 1, it finds the cointegrated levels in 0.13 of a second. If you add IIS, it takes quite a while to search across non-stationary variables with IIS, because if you don't have the right 10 in, it picks up lots of indicators to approximate them. But gradually the program finds them and drops them. And that's true even if you put in 50 lags, it finds them. And then what I'm going to show you is, having found the DGP, you now know it's cointegrated. You apply the equilibrium correction cointegration test that's been in PCGIV since 1975, which is a bit longer than 30 years, although it has different critical values these days, and we'll select in that. Okay, so this is switching live to Oxmetrics. So in order to slightly save time, I've set up the model. Well, sorry, Søren, I did that while you were talking. But it just is a matter to make sure I've got all the variables in. So we've got the change in YA as a function of 50 lags of the change in YA, the equilibrium correction that comes in up to 50 lags, and every one of the regressor variables up to 50 lags, all coming in, right? So that's 1,047 variables or something like that are continuous. Okay? Now we're going to do impulse indicator saturation. That creates an impulse indicator for every observation. So that's 4,050 of them. So now we've got, I think it's 4,050 because we lose 50 lags. So now we've got about 6,000 variables for the 5,000 observations. And we tell it to go. You can see it searching across all the blocks, finds something, searches across more blocks, finds something more, searches across more blocks, finds something more, and more blocks, finds something more. So it's beginning to come to large numbers, and now it's dropping back down to much smaller numbers, because it's now found some of the variables that matter. There we are. And I think that took 20 seconds. Yeah, 22 seconds. Okay. It's found equilibrium correction, and it's found all of the relevant impact variables, dza through dzj, and it has not retained a single irrelevant variable. And that's because at 1 in 10,000, there was only a chance of about 0.5 of keeping an irrelevant variable. And we just lucked out. We didn't get it. You can get it, but the most you'd get is about 1. So it's not a problem. It's very, very fast. Now, what about the M4 forecasting competition where the machine learners did not do well? That required you to forecast 100,000 time series, 23,000 annual, 24 quarterly, 48 monthly, and some weekly, daily, and hourly. You had to forecast them up to 6, 8, 18, 13, 14, and 48 periods ahead. And in order to deal with this, we created a new class within OCS. That's one of the beauties of having the program written in the software, the M4 class. And we then accumulated or aggregated results for each frequency. 248 people downloaded the data. Only 50 succeeded in entering. And I have to tell you, we met quite a number of them at the conference to discuss it. They just couldn't get it done in the 3 months you were allowed. Ours, generating forecasts for all 100,000 took half a minute. Didn't take half a minute's work to get to the models that then take half a minute to forecast. We designed new models that are machine learning within each series, but not across the series. We came 7th overall. We came 3rd on interval forecast accuracy, and 2nd on accuracy of the high-frequency ones, where you're going reasonably further ahead. So we did pretty well with our particular approach. Uber came first, those of you who are Uber fans. Uber looked at every series being a possible explanation within each series. So take the 23,000 yearly ones. When you pick one of them, they tried the other 22,999. And they did that for every series. Now, that's computation on a scale that most academics could never get hold of. And they did slightly better than us. We've implemented their method in a simulation. If you don't do that, we beat them all the time. And if you do that, they beat us. Now, this could be because some of the series have got leads relative to others, and they chance to find them, and then it's really powerful information for forecasting. But we think there's something else going on, and there's information of a very different kind in data than what people find when they look at factors. Okay, what conclusions do I draw? Many requirements to find sensible results from big data. You have to embed all the candidate variables in general initial models. Putting them in one at a time will get you nowhere. And this clearly favors big data and big methods. You need high quality data, and that could really be a worry for some of the analyses I see. I mean, I use DuckDuckGo. I never touch Google. I'm never going to show up in the Google trends that people were looking at. And that's true of lots of people now. And it's a pretty hopeless program in comparison. Enforcing very tight significance levels to avoid an excess of false positives. When n is large, that can cost you if t is small, but if t is large, it ought to be tight anyway. You need an effective selection procedure. You need to restrict the number of variables to selected over if you know what the theory is. And then you need to test that they're invariant. Autometrics tackles each of these in turn, formalizing the problem, selecting, evaluating, and the computational problem, as I've explained. Thank you.